Okay, can you hear me? Yeah. So thanks for the invitation to Didier. It's always good to practice English with French people. We have less pressure. So we will talk in this presentation about PLC. So I'd like to ask first who knows about PLC in this room. If someone knows, raise your hand. Okay, at least my ex co-director of thesis, hopefully. And so we'll talk about PLC and ERDF. So I don't know if you know about ERDF and the difference between ERDF and EDF. They are not the same company. So I will talk briefly about ERDF and after from PLC and one PLC standard, which is G3, which is the one that we use in the smart metering program in France, which is LINKY. So this is the electricity market in France. So it comes from the production to the customers. And so ERDF is what we call a DSO. This means a distribution system operator. And so this is the distribution level. So first you produce your electricity, then you transport it. This is RTE in France. And then you have distribution, this is ERDF. And then you have the supply, which can be EDF or direct energy and NG and the others. And then you have the customers. So ERDF is quite a big company. It's 38,000 employees with a comfortable turnover. And so interesting things here is that we have many kilometers of wire to maintain. In France, we have 1.3 million kilometers of wire. And so the idea of PLC, which means power line communications, is to transform the electricity networks into telecommunication networks. So we could have, in France, 1.3 million kilometers of telecommunication networks, actually. So this is the basic idea of PLC. So ERDF is moving toward its digital transformation through the LINKY Project because ERDF is a company which is working over electricity and it is moving toward communication. And this is not the same job. And so smart grids and other applications are the merging between electricity and telecommunication. And so guys like me that have done their PhD in Grenoble around telecommunication are actually needed in this company or other companies because they need some skills about telecommunication because this is not their core activity. So this is a kind of application we could have with LINKY meters. So of course remote control, adjustment between the production and consumption, and other applications. So we fast forward on this. So this is the LINKY meters. I don't know if it's green or yellow, so just ask the marketing. I don't really know, but I think it's green. And this is the key figures of the project. So it's a project over 6 years. So it's begin in the fall 2015. And it will end until 2021. So it's quite a big project because we need to roll out 35 million of meters in France. So there's two communication meaning in the project. PLC, this is what we will talk today, and 2G, 3G, classical telecommunication. So it's not insignificant cost, it's 5 billion euros, but actually half of the price is to install the meters. So if you divide 5 billion by the number of meters, this is not the price of the meters. And so this is a global architecture. So we have PLC on the low voltage networks, so it's 220 volt in France. We could have PLC on the medium voltage, but it's outside the scope of this project. And so we install a data concentrator in what we call secondary substation. This is what transforms the high voltage, the medium voltage, in low voltage. So you have this data concentrator, and it collects all the meters connected on the low voltage part, and it then sends all the data to the system of information of ERDF. And so the rollout strategy, so we are here in the beginning of 2016. So we have two PLC standards. This is G1 and G3. I will talk about G3, but G1 is an old technology, I will say, and G1 is a new one. But it's hard to send a new technology for such a big project in the first time. So we are in the mix of G1 and G3, but you see that after 2017, you only have G3 meters. So at the end, we will have 32.5 million of these G3 meters, and the other part will use G1. So we are deploying, we started 1st December of 2015, and they find a name for this kind of rollout, which is leopard pattern rollout. Yeah, okay. So that means that we deploy everywhere. We could have done it region by region, but it's all in the same time until 2021. So let's talk about PLC. So PLC means power line communication. And so there are many ways to communicate. You can use wireless antenna, you can have dedicated wires like Ethernet cable that are made for communication, or optic fiber. The electric wire is not made for telecommunication, but we will see that we can use it. So the choice of PLC is pretty natural for ERDF because we maintain the networks. So at actually no price, we could have these telecommunication networks. So that makes a lot of sense for DSO like ERDF, and actually in the world, a lot of projects to collect meters are using PLC communication, and some of them are using G3. And yeah, one big things to know about PLC is that, of course, you are independent from the telecom operators. That means you don't have to pay to transmit the data. Because if you buy 35 millions of SIM card, that costs quite a lot compared to here, wire that is here and you can use for free. So the basic idea is you have those electric signal, which is 220 volts and 50 hertz in France, and you add a higher frequency signal with a very low amplitude. This is below 1 volt. And so, at the end, on the wire, you have these red curves. So you have the 50 hertz high voltage and the higher frequency small amplitude signal. So this is actually seen as a noise by your electrical appliance. This does not disturb at all your equipment because actually you already have such noise on the electric field. So it's just another noise, but it is data for us. And so, of course, you have pros and cons using PLC. So I already talked about the pros, which is the communication support is ready to use. One big thing to know is that the grid is actually just the largest wired network on Earth. And so it costs a lot to wire networks. And so it would be a shame not to use it. In Europe, we have a big advantage because we have a reserved frequency band, which is called Senelec A. And this is something that the telecom operator will dream about, is that we have this band for free, and we're the only one to use it. So it's great. And yeah, so the grid is maintained by us, so it makes sense to use it. And the cons, of course, is that because the media is not think to be used for communication, then you have side effects like disturbances or noises that are created by appliances that you may connect on the grid. And also this is an open media. Like I can access PLC through this electrical socket. So there's big concern to think about security, of course. So this is all the different PLC technologies and frequencies that you can use. So I will talk about G3-PLC, which is here. And in Europe, we use Senelec A. So frequency is from 35 to 90 kilohertz. But we may use G3 on other frequency bandwidth, like in US, you have a larger bandwidth. This is FCC. And in Japan, they have a larger bandwidth. So in France, we use this frequency bands. So yeah, so G3 is using the IPv6 protocol, and so the IP, in fact, is what makes the global internet working. So I see G3-PLC using IP like an extension of the IP networks. Because as you know, so internet relies on IP, and if you use it, then you can connect other devices. And IP is sometimes seen as what we call the narrow waist of the architecture. When you have multiple technologies on the physical level, you have several applications, and on one point you have one single protocol that can be IP. And so actually, this is all the partners that are in the different alliance. So we create an alliance called G3-PLC Alliance, and this is all the partners that are inside the alliance. So you see a lot of them, a lot of famous names, and you see them in other alliance. And what we see here is that we have some different manufacturers, and so this means that we have to do some interoperability, and this is the global idea behind a standard, is that you have to have interoperability. So this is the number of certified platforms that we have on the Alliance. So we have now 73 devices that are certified using G3. So it's quite a big number. And so this is a global stack. So the technique people will like this slide because they will see a lot of technologies that are used in the IoT. So you see 15.4, you see 6LoWPAN, you see IPv6. So this is very similar to what I studied actually during my PhD. This is all the IoT classical stacks, but the main difference, of course, is at the physical layer, because we are using PLC. And on the application side, we use what we call the LMS COSEM, but we could have other application protocol like CoAP and other one. If you are interested into the specification, you can download it. This is G9903. You can have it on the ITU website, and you will have all the description of the protocol. So this is what G3 looks like. So this is an evaluation kit from Renesas. So this is a classical device. Like I have an MCU, I have a modem. The only difference is that we have a coupling to be connected to the electrical wire, but also on wireless devices you also have coupling with your antenna. Here this is just another kind of coupling. And so if we describe a little bit more the physical layer, we find quite low throughput, and this is quite similar to what you have in 15.4 or IoT devices. So it's not the throughput in the next slide, but you have OFDM modulation. This is used in other technology like Wi-Fi, but we use it on PLC. So we have 36 carriers in the SNLK band. And we have different modulation that enable to have the good trade-off between robustness with low throughput and high throughput but less robustness. And this is negotiated on each link depending on the behavior of the link in the time. And you have classical error connection and time diversity that enable you to recover the bits that you may lose during a transaction. So if you plug an oscilloscope on the grid, and when you have V3, you see signal like this. So you see it's low voltage, it's below 0.5 volts. And you have a preamble that enable all the devices to synchronize. And then you have the data in a second time. And if you see on the frequency domain, you have this type of shapes. So you find the 36 carriers I'll talk about just before. And you have here the frequency, the throughput, sorry, I was talking about. So it's from 4 to 44 kilobits per second. So it it's not so much, but it's enough to collect a meter once a day. And this is in the same range that what we have in IoT networks, basically. We have some specific services compared to 802.15.4 that you may know. So we reuse a lot of it, but we added some services to be compliant with the specificity of PLC, which is, for example, the tone mapping, which is the ability to negotiate a modulation for each transmission to be sure to have the best modulation available, and independent on the noise or on the level you may have on each carriers. And also we need routing. So this can be strange to say, okay, if I have a wire between all my nodes, normally I should be able to communicate between all the pair of nodes because there are the wires between them. But actually it's not the case, because you have some attenuation and noises, and so you cannot, from a single point of the network, reach all the other points. And for example, this is a graph that is coming from a real networks. And so between the black point and this point, I cannot communicate directly, so I need routing. And so this is done by a protocol which is LoadNG, which is inside the standard. And so this enables you to find the best route according to a routing matrix, which can be the throughput or the quality of the signal, and other metrics are available in the standard. And so it enables you to build a path between your concentrator and all the meters, and to rebuild the route if the link breaks, because it happens like in every IoT and non-reliable networks. So if we focus a little bit on what's going really on the field, so this is a graph that is made from neighbors tables collected on a real networks, and this shows all the links that you can have on a real networks. So that's a lot. And the numbers you have inside the circle is the percentage of meters with which a PLC communication is possible. So for example, this big blue guy can communicate with 60% of the networks. So it's not 100%, that means you need some routing, but that means also that you have a lot of paths possible to reach all the meters. So it's a good news, because if a link breaks or is not reliable, then you have a backup to communicate with the others. And so this is a bootstrapping time of networks of 133 meters. So we have done it in a laboratory, because if we want to do this on real, we have to shut down all the customers and then shut it on to see this curve, so the customer won't be very happy. And so we do it in the lab. And so it takes less than half an hour to bootstrap all the 133 meters. And so you may think it's a lot, but actually there's all the security mechanism involved in this curve, where you have EAP PSK messages, exchanges with authentication and session that are open. So it may take some time, and after all, you do this one time. I mean, you plug the meter, it boots, it bootstraps, and after it's done. So this is a very particular situation that are not happening so much on the field. Just happen during like storm, where you have the electricity that's coming up all in the same time. So this is actually the biggest network we have in France. This is in Nantes, in the island of Nantes. So we have 463 meters in these networks. So it is seen by Google Maps, but Google Earth, but this is big buildings of 16 floors. And the data concentrator is here. And so we have one network of 463 meters. And so here are the performances and the characteristics we have. So this is a number of neighbors that you have distributed in the networks. So the concentrators, for example, is seen and see more than 200 meters. and we see a peak at 100 nodes, so that means that most of the nodes see at least 100 nodes on the field. So it's pretty similar to the graphs I saw you just before. So for us, it's good to know it because this means that we have a good range, and if we have just one node that is seen by another one, this means that if you lose this link, then you lose a connection. And so this is a number of hubs we have on these networks. So most of the nodes are reached at 2 hubs. That means you need one forwarder, one router. And within less than 4 hubs, you reach all the meters within these networks. And this is a modulation distribution. So we see that most of the links are using D8-PSK, which is the highest throughput possible, and that means that you have actually good link because you can use this modulation. If all the modulation were robust, this means this is very hard to communicate, the throughput is low, and it's very hard to communicate. So this is a collection rate. So we have a target of 95%. This is fixed in the law, actually. We have to collect at least 95% of the matter each day. And we are at 98.6, which is pretty good. So yeah, to sum up, we are very happy and so on, okay. Of course, or I won't be there. But there's still room for improvement. Okay, we want to reach 100% collection rate, but then you can push beyond the performances. So we may tune the parameters or maybe increasing the data concentrator request rate to collect them, but maybe faster, and have bandwidth for other services in the future. And also, now, if we look at the perspective, like, okay, we have this system, it collects a lot of data, but then what could we do with it? So one application we have is that we build actually the cartography of the grid using this data. Because you have routing, then you can have like a network map of the grid. And this is another information sources for ERDF that can be compared with the topology, the electrical topology, and we see if we see differences, that this means that there could be a mistake inside the cartography. So we can correct cartography mistakes by using the PLC routing or PLC path that we collect on the field. And so this is a kind of beautiful graph we do. So this is a connection graph on the field. We use community detection to have like the topology, the communication topology of the grid, and then we mix with color with what we have in our bases. So here, for example, I have the red community. Red community is all the meters that communicate very well between each other. So that means they are connected on the same wire. And the color is from our cartography services. So here we see yellow point in the middle of red points. That means that the cartography says they are on the same topology, and these ones are not on the same wire. So there should be a mistake somewhere, because cartography says they are not on the same electrical wire, and G3 says they are on the same. So we can detect error and correct it using this data. So this is just an example of application, but we may imagine a lot of other applications with all the data we are collecting each day. I think this is the end. Yeah. So if you have any question, we'll be happy to answer it.